Hi everyone, welcome back to my channel, The Space Koala. My name is Lutza and today we're going to be talking about the colorful world of astrophotography. More specifically, we're going to be getting into what exactly it is that makes it so colorful. Let's get into it. A few weeks ago, I posted a short video on social media that was meant to be something funny and lighthearted, kind of making fun of the amount of effort that goes into making astrophotography images palatable to the average person looking at them. And this ended up sparking quite a bit of controversy, with people claiming that the photos are fake, space is fake, NASA is fake, it doesn't exist, just because I shared actual raw, unedited images that were black and white, and then I showed the corresponding final image that was in color. Well, today I'm gonna try and clear all that up, and I'm gonna explain in detail how exactly I turn those monochrome images into the beautiful, colorful, lovely astrophoto images that we all like to look at on the internet and on social media. Let's start with how a monochrome camera works with filters. Unlike regular color cameras, monochrome cameras capture images in black and white. This might seem counterintuitive for capturing beautiful, colorful images of the night sky, but there's actually a really good reason why many serious astrophotographers prefer this method. Monochrome cameras have sensors that are highly sensitive to light because they don't have the colorful bare filter that color cameras have. This means they can capture more detail and more light, making them perfect for deep sky astrophotography. To look at the simplest case, to capture color information, we're going to be using three filters: a red, a green, and a blue filter. These filters are part of what we call RGB imaging. Each filter blocks all other colors of light, and it lets through only its own specific color and lets it reach the sensor. This means we can take multiple shots of the same object with each filter separately. Here are the filters and the channels taken with each filter. The red filter captures all the red light and all the detail seen in the red light. The green filter captures the green light, and the blue filter the blue light. This process is crucial because it allows us to record the entire spectrum of visible light in great detail. What we tend to do is we put these filters into a filter wheel, which is just a tool that lets us swap filters in an automated way, and then that connects to the camera. It has a single opening, and we can swap out the filter, always just letting one of the colors through, and that's the one that's going to reach the sensor. By taking multiple exposures through each filter, we gather all the color information needed to create the full color image. You can imagine it a little bit like painting. Each filter represents a layer of paint, and only through layering all the colors we're going to get the entire complete full spectrum color information. By the way, red, green, blue is not the only way to combine colors. For example, small photo printers usually work with cyan, yellow, and magenta. They're mixing those colors. This is subtractive color combination, whereas RGB is additive. But now let's combine these channels. This is where the magic happens. By aligning these already stacked images of each filter, we can reconstruct the original color of the target we photograph. One of the main benefits of using a monochrome camera with filters is the ability of gathering more light and more detail. Since each filter just lets in one specific wavelength of light, we can expose for longer without worrying about light pollution and other sources of noise. This can result in clearer and sharper images. The other two main benefits of mono cameras, which convince a lot of astrophotographers to switch over from color to mono cameras, are the following. First is the ability to shoot what we call a luminance layer. This is taken with an additional filter, the luminance filter, which lets through the entire spectrum of visible light without filtering out any of the specific colors. This, of course, loses the color information, but in turn, it collects about 3 times as much light in the same amount of time compared to the individual color filters. Then, using astrophotography software, we can use this new luminance layer to add more detail, more clarity, and reduce the amount of noise present in the already captured RGB image. This, of course, then means that overall we took less amount of time to capture the same amount of photons compared to a color camera or using RGB filters only. The other huge benefit lies in the use of narrowband filters. Emission nebulas, supernova remnants, and planetary nebulas all emit radiation light in only extremely specific wavelengths, which then of course can be separated with ease by using what we call a narrowband filter. For example, a narrowband filter used for hydrogen is still red. However, instead of letting through a band of 100 or 200 nanometers width band of wavelengths, depending on the preferences and the budget of the user, it can go down from 20 nanometers all the way down to 3 nanometers. This in turn makes it possible to capture photos of these objects without worrying about virtually any incidental light, be it natural such as starlight or moonlight, or artificial such as light pollution. Of course, the process of aligning and stacking images is in any case crucial in astrophotography. Regardless of the type of camera used, there is an additional step when using a monochrome image because the individual stacks of the different colors representing the different channels of the final image also have to be aligned with one another before they can be combined to give us the final color image. A lot of people asked how I can possibly be sure that these are the real colors of the images, and I think this is a very valid question because simply by putting together the 3 filters, there's absolutely no guarantee that the 5 minutes of blue and the 5 minutes of red and their respective differences in intensity per pixel actually correspond to the target, because it could be due to an unlimited number of other factors that are beyond my control, such as changes in the lighting conditions, changes of transparency of the sky, the moon was in a different position, there are street lights which are not exactly white light but are more blue or are more red. This is when color calibration comes in. More specifically, the only tool that anyone should be using in 2024 for calibrating color images is spectrophotometric color calibration. We are lucky enough to live during a time when we have a number of professional telescopes and space telescopes out there taking spectral information of millions and millions of stars. This data is then published into publicly accessible databases that anyone can download on their computer. We then have software that can match the stars in our image to a series of stars for which we know the exact spectrum, meaning we know exactly what color it should be, and then we can apply scaling factors on the 3 channels RGB to make sure that the final image has exactly the correct intensities. After applying this step, we can be 100% sure that the colors in our image are actually true color. This is not something that was created by AI. This is not something that I created based on my liking. This is the true actual image that has been calibrated with a scientific approach. This process will help us get rid of any bias that was introduced either by our equipment, incorrect calibration, or by the atmosphere itself. This color calibration process is not just crucial in astrophotography. It is also crucial for research because without being able to see the true spectrum of the colors that were recorded, one might draw the wrong conclusion, and it is just not appropriate to do science that way. That said, sometimes we actually go out of our way to create non-true color images in order to be able to highlight specific features in our photos. The most famous and by far most popular method is called the Hubble palette, also used by the Hubble Space Telescope. The Hubble palette assigns different colors to specific elements. For example, sulfur is mapped to red, hydrogen is mapped to green, and oxygen is mapped to blue. These are not the true colors that you would see with the naked eye if these objects were bright enough for us to be able to see them, but they are a crucial part of the scientific process because it allows us to see structures better, because both sulfur and hydrogen are red, so our eyes would not be able to separate the structures of hydrogen and sulfur. Whereas using this technique, we can see much more detail and we can understand the structure of the nebulosities better. Not to mention, as astrophotographers, it also gives out a much more balanced and beautiful and colorful image. Here's a comparison of the same photo that I took when it was processed using a true color palette and the other one using a Hubble palette. The true color image shows what we would see with our eyes if our eyes were way more sensitive. The Hubble palette is widely used in scientific research because it helps astronomers identify and quantify the amount of specific elements in celestial objects. Here we see some of my images captured in the Hubble palette. This is the center of the Heart Nebula. Here we have my version of Hubble's Pillars of Creation. This is a part of the Soul Nebula. This is the central region of the Rosette Nebula. This is the Elephant's Trunk Nebula. See that each of these is quite colorful, and whereas the true color image would be 95% just red because by far hydrogen is the most abundant element. Overall, I'm an absolute fan of the Hubble palette and this technique because it allows us to capture breathtaking photos of the universe, which are very balanced and aesthetically pleasing. Not to mention, the most important benefit is that it is used for science to understand our universe better. Now, let's talk about how color cameras work. Color cameras use what is called a Bayer filter mosaic over the sensor, which covers each of the pixels with either a red, a green, or a blue teeny tiny filter. In a Bayer filter, half the pixels are green, a quarter are red, and a quarter are blue. This mimics the human eye's sensitivity to light because we are most sensitive to green light. It's just because the green color is the center of the entire spectrum of our sun, and therefore it is a benefit for us to be extremely sensitive to green light. Then we have this Bayered image coming out from the camera, and we usually don't even tend to see this process because any type of camera, smartphone already does the process for us, but there is a step needed from a raw image to getting the color image, and this process is called debayering. As each of the pixels only records one of the three possible colors, we have a lot of missing values that are actually never measured. They're interpolated by software. What that means is that the software takes the most probable value for that pixel. If you have a 24 megapixel sensor, you don't actually have 24 million of each of the three colors. You have 12 million green pixels and 6 million red and 6 million blue pixels. Then the software will assign the most likely value to each of the missing colors, and this is how we end up with a color image. Obviously, color cameras are more accessible and intuitive for most use, especially for daytime photography, but also for many astrophotographers. However, it is important to keep in mind that they do have a very important limitation because of the fact that they have this Bayer filter in front of the sensor, and that is that they only allow part of the light to reach each pixel on the sensor. The Bayer filter array actually reduces the amount of light reaching each of the pixels, resulting in less resolution, especially when working in low light conditions, such as what we do in photographing the night sky. This interpolation process can actually go wrong, and it can introduce a lot of errors and color artifacts, which then also results in much less detail in the final image. While color cameras have their limitations, there are, of course, a lot of ways to mitigate these problems, both by taking extra care during the image capture process and by fixing some of these possible issues that are introduced in post-processing, ensuring that we use high quality optics that don't introduce additional color aberrations, and applying some of the same post-processing techniques as what we have seen before, such as color calibration. We can mitigate most of these issues. Not to mention, there's been so much advancement in technology, both in the sensors themselves, the Bayer filters applied on the sensors, as well as the debayering algorithm used by the different software, that a lot of these gaps are being narrowed down between color cameras and mono cameras. This will never change the fact, however, that the most correct way to take astronomy images, especially those which will be used for scientific purposes, is always going to be using filters on a monochrome sensor. Every time we use interpolation during the processing, we are subjecting ourselves to an error. Avoiding interpolation altogether is the best way to ensure that we are not introducing errors during the processing. By the way, it can also be done by debayering a color image using the superpixel method, which instead of guessing the missing pixels, it just puts the existing pixels together, resulting in a much smaller image. However, this much smaller image only has actual, factual, correct color information that's been recorded by the sensor. Putting together all this information that we've gone through, it is easy to see why a lot of astrophotographers would still prefer monochrome cameras, both due to the quality and the resolution that can be achieved, and also due to the actual time savings that can be achieved. For example, if we think about those narrowband filters mentioned earlier, especially the 3 nanometer hydrogen filter that we said, if we put that 3 nanometer filter, which lets in a small fraction of red light only, we put that in front of a color sensor on which only a quarter of the pixels is going to record red light, results in an extremely inefficient way of taking pictures. Not only are we filtering out most of the incoming light, which is a good thing because we're filtering out all the things we're not interested in, but we are only using a quarter of the sensor of the camera. Naturally, this is usually mitigated by modern dual band, even quad band filters that let in multiple bands of narrowband image so that we can use more of the filter. There's a lot of advancement closing these gaps. However, getting back to the example of the Hubble palette, we will never change the fact that hydrogen and sulfur are both red. So even if we have filters that are selective enough to separate those, we will never be able to record them at the same time because we need the red pixels of the color camera. I took this one with a mono camera. This is my personal preference to use mono cameras for the most part, not always. I will always be using a color camera when shooting the Milky Way. There's just no benefit there for mono cameras. I will also continue to be using a color camera when it is really inconvenient or impossible even to swap filters. For example, when using my Rasa telescope, where I just can't put a filter wheel in front of the optics because it would be blocking half of it. Not everybody wants to deal with mono cameras. There is also an entry barrier to mono cameras because while the price of a similar sensor in color and black and white is almost similar, in addition, one does have to buy the filter wheel and the individual filters, which depending on the brand and the size can range from a few $100s for a whole set to even $10,000-$15,000 for those extremely high-end filters that I don't have, but a lot of people do. I'm aware that a lot of people make the argument that they stay with color cameras because they just don't have the time to capture enough images for mono. This is the only argument that I don't agree with because we have seen how it is actually more efficient. It takes less time to take the same image with a mono camera versus a color camera, but it does take longer to process it. This is something that I personally don't mind. I do hope that this short video helps clarify some of the concepts, why mono cameras do not create fake images, and how we can be sure that the colors that we capture are the real ones. Whichever camera you use, astrophotography is not pure science. It is also art. Everybody has their own preferences and editing style, and there's absolutely nothing wrong with that. We can also create any type of false color image. However, I do think that any non-traditional editing techniques should be declared if a photo is published on a forum of scientific interest. Whether you're a color or a mono person, I wish you a lot of clear skies for this upcoming summer, at least in the northern hemisphere. Nights are getting very short. I'm also hoping that the weather is getting better. Thank you, and till next time, clear skies.